All right, today we're planning something, well, something pretty wild. We're gonna pull off the ultimate cosmic heist. And our target? A black hole. The goal? To steal its energy. Yeah, you heard that right. So let's figure out how on Earth that's even possible.
I know what you're thinking. How can you steal anything from a black hole? I mean, it's the universe's ultimate endpoint, right? Gravity so intense that nothing, not even light, can get out. So taking something from it, that just sounds impossible.
And for a long time, the answer was simple. You can't. It was thought to be absolutely impossible. Ever since Schwarzschild's work way back in 1916, we've seen black holes as this cosmic one-way street. You cross that line, you're gone forever. The universe's most secure vault, period. But you know, every vault has a blueprint. And if you study that blueprint long enough, you might just find a weakness. It turns out, not all black holes are created equal. And that little difference, well, that's the key to our impossible heist. Okay, so you've got two main types of these cosmic vaults. On one hand, you have your standard, non-rotating black hole, a Schwarzschild black hole. Think of it as a simple, static prison. Nothing gets out. But then you have our target, the Kerr black hole. This one is different. It spins, and it spins fast. And that rotation? That changes everything. It's not just a prison, it's a potential power source.
So, back in 1963, a physicist named Roy Kerr figured this out. He found a whole new solution to Einstein's equations that describe these spinning black holes. And that spin, that angular momentum, that's the power source we're looking to tap. The secret isn't about breaking into the vault, it's about using the way the vault itself is moving.
And here's the crazy mechanism that makes it all work. It's called frame dragging. A spinning black hole doesn't just sit there in space. It literally twists the fabric of space-time around with it. Imagine a spinning ball in a big tub of honey. It drags the honey around with it, right? The black hole does that to space-time itself, creating this massive cosmic whirlpool. And that is where we find our opening.
So, to pull this heist off, we really need to get to know the layout of our spinning target. It's not just one big point of no return. There's this really fascinating, and for us, absolutely crucial, in-between zone.
First up, you've got the boundary that everyone's heard of, the event horizon. You cross this line, game over. You're never coming back. So that part of the black hole's security system is still very much active.
But outside of that event horizon, on a spinning black hole, there's this bizarre place called the ergo region. In here, the frame dragging is so intense that space-time itself is being dragged along faster than the speed of light. Now here's the kicker. You can actually enter this region and still get out. If you play your cards right, you can escape. This is our loophole. This is the chink in the armor. So, let's be super clear about this. The ergo region is everything. It's the stage where our entire operation is going to take place. It's this weird little pocket of the universe where the laws of physics get just strange enough for us to exploit them and hopefully walk away with a massive energy payday. Okay, so how do we actually do it? Well, physicists have come up with two main plans for this cosmic stick-up. The first one, dreamed up by the brilliant Roger Penrose, uses particles. The second one, it uses waves. Let's kick things off with Plan A, the Penrose process. This is just an incredibly clever bit of physics that basically turns the black hole's own rotational power against itself. So here's the breakdown. First, you fire a particle into the ergo region. Then, once it's in there, you split that particle into two pieces. Now this is the genius part. You design the split so that one piece falls down into the black hole with what physicists call negative energy. Now what does that mean? From our perspective, way out here, it's like that piece is subtracting energy from the black hole. And thanks to the law of conservation of energy, if one piece has negative energy, the other piece has to have more energy than the original particle started with. That second piece gets flung out, escaping with all that extra stolen energy. Boom. Now the Penrose process is, well, it's theoretically beautiful, but trying to actually do it, it's a technical nightmare. Imagine trying to fire a particle and split it with that kind of precision. So you gotta ask, is there an easier way? What if instead of particles, we just used waves?
And that brings us to our second method, something called superradiance. It's a really cool idea. Instead of a particle, you just shoot a wave. Could be light, could even be a gravitational wave, right at the spinning black hole. If you get the properties of that wave just right, it doesn't just bounce off. It actually gets amplified. It comes back stronger, stealing a tiny sliver of the black hole's spin energy in the process. And this quote right here just nails the core idea. In physics, right, a reflection coefficient of 1 means you get a perfect bounce, like a perfect mirror. A coefficient greater than 1, that's supposed to be impossible. It means what you get back is more powerful than what you sent in. You're literally getting more out than you put in.
Okay, so we've got our methods. We can use particles, we can use waves, but here's the catch. This is not an infinite power source. This heist has a cost, and there is a very, very specific limit to how much we can actually take. See, this energy isn't being created out of thin air. We're not breaking any laws here. We are directly siphoning off the black hole's angular momentum, its spin. So with every single particle, every single wave we use to steal energy, we slow that black hole's rotation down just a tiny, tiny fraction.
And here it is, the big number, the absolute limit. Using these processes, you can only extract a maximum of 29% of a black hole's total mass energy. That number represents all of the energy that's tied up in its rotation. Once that's gone, the vault is empty. The heist is over.
And if you look at this, you can see the before and after picture pretty clearly. Before our heist, we have a fast-spinning Kerr black hole, and it has that all-important ergo region. But after we've sucked out all that rotational energy, the spin is gone, the ergo region vanishes. Our target has literally transformed into a standard, non-rotating Schwarzschild black hole. And all that's left is what we call its irreducible mass, a core mass you just can't tap into any further.
And thinking about this leads to some truly mind-bending applications. Like, for instance, what if you use gravitational waves for this? You could theoretically create a gauzer. Yeah, not a laser, a gauzer. A gravitational wave amplification by stimulated emission of radiation. You'd be amplifying gravity itself. Wild.
Which, leaves us with one final, pretty tantalizing thought. Are we basically looking at the blueprints for the power plants of the distant future? Could a super advanced civilization actually harness these cosmic engines to power entire worlds? It sounds like something straight out of science fiction, but it's not. It's real, theoretical physics.